We have seen the relation between pressure, volume, temperature, and the number of moles. We have seen that these quantities can be related by this equation, which is called the ideal gas law. Now, what I like to do now is to think about the molecules or atoms, right, that make up the gas. I want to find a way to relate the properties of these molecules. Say if it's oxygen, the property of the molecules, meaning its mass and volume. Okay, it's mass and not volume, velocity. It's mass and velocity to say the pressure, the temperature, and the volume. This is in the hope that we can get a better understanding of the energies involved and the reasons why we have temperatures and pressures. So let me start. Now I'm going to think of a simple box. Say a box like that. Okay. Now this is the side view of the box. The box might actually is a three-dimensional thing. Okay, but for now I'm not going to worry about the other sides. I'm just going to think of a particle when I look from this side. Think about a particle. Say this is a particle of oxygen molecule. Right? I'll still follow the example of a oxygen molecule. Well, actually, there are lots and lots of oxygen molecules in this box of oxygen gas, and they're all, we can imagine that they're all moving around in all sorts of directions, all random directions, and they bounce around and they have different velocities. Now, for this exercise that I'm going to do, I'm going to make some assumptions. All right, like I said, I want to try to relate pressures and temperatures to the properties of the mass. So let me maybe write down this aim. It might seem a little bit grand or ambitious. I want to relate the pressure to the mass and the velocity of the molecule. I want to see how I can do that, or at least come close to doing that. So in order to do that, as I've described, there are lots and lots of molecules and it's all very complicated. So how can we ever how can we ever dream of actually calculating such a complicated thing? Right? In physics, the way to do calculations, the way to estimate physical quantities when the system is very complicated is to think of some ways to simplify things. Now, in this case, we are going to make a few very simple simplifying assumptions. Now, I'm going to write this down. Assumption. So the assumptions that we're going to make to make the calculations easier. That's one thing, and to help us also to understand, maybe not immediately, but maybe later on, to understand the system better. So we are going to assume a number of things. Right, we are going to assume that the particles in this gas. So particle in this case would be the molecule. The particles, meaning the molecule, are very small. Okay, now what does that mean physically? Very small means that it is very unlikely for them to bounce into one another. So the particle would just travel round and bounce round and round between the walls of the box and hardly ever bump into another particle, even though there are so many of them, because the particles are so very small. Okay, then the next thing I'm going to assume is that particles are very small, so no collisions. Okay, no collisions. Now the next thing I'm going to assume is that there are no attractions between the particles. Now we would expect usually, because the molecules are made up of electrons around the nuclei of protons and neutrons, these electrons and protons have electrical charges. So it is usually possible for some attraction to happen between one molecule and another in a real gas. But what we're going to do for assume here is we're going to assume that these attractions that there are no attractions. All right, in a real gas, there would be some attraction, maybe small, but here we're going to assume, just to make things simple, right? No attraction between particles. Now we can see where we are heading. All right, we can see where we are heading. Generally, basically these two assumptions basically assumes that the particles they can move around completely unaffected by other particles. So as far as this one oxygen molecule is concerned, it would move around as if all the other billions and Avogadro constant number of molecules are not there, right? As if it's on its own, right? Because of these assumptions. And you can see why now that these assumptions simplifies things, because all I need is to just look at the motion of one molecule, and then I can have some hope to understand what's going on. All right, if I can understand one molecule, then I just need to multiply by somehow add up the effects of the other molecules. For example, if I can find the pressure due to one molecule, right, I'm actually going to do that afterwards. If I can find the pressure on one mole due to one molecule, then all I need is to multiply by the total number of molecules, and I would have the total pressure P. So you can see now that it's looking more likely that I can actually find a relation, right? Which actually means find a formula for the pressure, to calculate the pressure in terms of mass and velocity of the molecule. So let's start. Right, with this assumption, okay, I know that now I can just look at a single particle. Now, while we are on this assumption, let me write down a name. Now, if I make this assumption, right, if I make this assumption of a gas, then a gas which obeys this assumption, which agrees with these assumptions, or satisfy this assumption, a gas which satisfies this assumption is called an ideal gas. Ideal. Now, I am not exact ideal gas or perfect gas. Perfect gas. There are two names for this. Now, I'm not exactly sure in what sense a gas is ideal or perfect in the everyday sense, right? As far as I can see, it is ideal or perfect in the sense that it is perfectly simple or ideally easy to do calculations and to think about it. That's all. Okay, there isn't anything perfect or ideal in the everyday sense, right? So perfect and ideal really means basically very simple or simplistic. Okay, and for this reason, it's for the same reason that we had the ideal gas law that we saw previously, and later on we'll see how all these assumptions are connected to the ideal gas law. So for now, what I'm going to do is to think about this one oxygen atom and to see if I can find the pressure due to one atom, one molecule. Okay, that is a pretty unusual thing to do because we normally think of pressure as from a gas as the result of lots and lots of molecules hitting on a wall or on some surface. But now I'm just going to look at one single molecule. So what I'm going to do is I'm going to say, right, suppose that this molecule has a certain velocity in a certain direction. I'll call that C. Now, the letter C is also often used to represent the speed of light. Okay, we often see this letter C used to represent the speed of light, but C actually is also used in other areas of physics, like this one. So in this case, C is not speed of light. C is just the speed of a molecule. Okay, so it can be typically in any random direction with some value. So what I will now do is this. I want to try and find the pressure due to this molecule on one wall. So this means that I could just consider the components of C in a direction that is perpendicular to this wall. Okay, so let's say this is the component along this direction of C. I'll call this U. Okay, and let's say the mass of the oxygen molecule is M. And as I said, we're interested in pressure. Now, let's see how we can make a connection between pressure and, say, mass or velocity. The way to find a connection, all right, between different quantities is usually to start by thinking about the definitions of each quantity. So let's start with pressure. Pressure is equal to the force divided by area. So in this case, this is the area that we're talking about. This area, it's on this wall, and force, in the definition for pressure, force refers to the force perpendicular to this wall, right? Which is why we should consider this component of the velocity that's perpendicular to this side. So okay, so now I have pressure in terms of force and area, and now let's think. Force and area, right? I have two quantities here. Is any of these related to mass and speed, velocity? Indeed, yes. Force is related to speed, or to velocity and mass. If you recall Newton's second law, let me write that now. Newton's second law says that the rate of change in momentum is equal to the force, or is proportional to the force. Right? And rate of change of momentum means change in momentum. So we're talking about, let's say, an object has a initial momentum of mu, like this one, okay, and maybe after experiencing a force, say its velocity changes to v. Okay, so the change in momentum will be the final momentum minus the initial momentum after a force acts on it, divided by the time in between this change.